So I would like to continue now the discussion of thermometry in the gas phase. And already mentioned, we have three classes of thermometry, and we will start with that one based on the Boltzmann distribution. And as I already mentioned, we restrict ourselves here to diatomic molecules, where we have internal degrees of freedom, which are electronic excitation, vibrational excitation, and different rotational energy levels. And so for a diatomic molecule, you see here a chart, a scheme showing the different energy levels over the internuclear distance. That is the distance between, for example, these nuclei, let's say in NO, between nitrogen and oxygen. And in most of the cases, it is sufficient that we just consider the electronic ground state, that is called X in all the cases, and the first electronic excited state, which is called A. You would have then a second electronic excited state, which would be B, the third would be C, and so on. And we will see that in many cases it's sufficient to look at X and A. Each of these electronic states is split into different vibrational states, meaning that you have here as well discretized energies of vibrationals, where all the energies in between here, they are not allowed. They are not accessible. So this is one of the main results from quantum mechanics applied to molecules. You have discrete levels of energy with respect to the electronic excitation, with respect to the vibrational excitation, and with respect to the rotational excitation. So each of these states does have as well a rotational substructure, where you have here as well, this is the energy again in vertical direction. You have here different quantum numbers for the rotation. And there are as well discrete values, and they're nonlinear increasing with the J number, which is given here between 0 and 4. Of course, they go up to infinite. And the outcome that we need from molecular physics is that you can calculate for a molecule its energy, contained energy in this degrees of freedom with the electronic energy. The next three terms are the vibrational energy, given by this omega E, Xe, and Ye. You will find that in tables for specific molecules, independence of the vibrational quantum number V, which is shown over here, from 0 to infinite. Whereas the first expression over here, V plus 1.5 to the power of 1, that is due to a harmonic oscillation, and these two other terms are the so-called anharmonic corrections. And anharmonic corrections you can directly see. This is a potential which is maybe here in its bottom close to a harmonic potential, and then you see the deviation from the harmonic potential. This is corrected by these terms number 2 and 3 in this expression, omega E Xe and omega E Ye. And then you have superimposed to that the different rotational levels given or denoted by the rotational quantum numbers J from 0 to infinite, and the rotational constant B, and the correction here D means that the rotator is not rigid, but if you have higher rotational energies than what you would expect, of course this is a system which is not rigid, so if you rotate that stronger, the two nuclei will have a larger distance, and thereby the rotational number is decreasing, and that is simply corrected by this second term for these rotational energies, which is as well here at higher order, similar to here. So the corrections are second and third order, and for the rotation it's only second order, which is sufficient to account for this non-rigidity. And that means for a given molecule, you will find the energy needed for an electronic excitation, and you will find all these numbers, omega E, Xe, Ye, B, and D, with which you can exactly calculate the energy of that molecule for a given quantum state. And so spectroscopy is all about now that you change these quantum states. For example, by absorption, if you shine in a photon, this photon can be absorbed by the molecule, and the energy of this photon is transformed into internal energy of that molecule. For example, going from the electronic ground state to the excited state, going from the vibrational ground level, in this example here, to the second vibration level in the final state. And of course, this absorption can be used, we will see later, to probe the Boltzmann distribution prior to this disturbancy. Okay, so we have now to look into more detail into this Boltzmann distribution for diatomic molecules only for this different degrees of freedom. So once again, what you see here is the Boltzmann distribution as given before, but what is different now, we refer ourselves here to rotational levels. That's why you find here the rotational quantum number J. If you compare it back to what we have had here, this is the general formulation, and now we specify that for the rotation. And then this is the rotational energy, which can be calculated by this expression. So we know that as well for a molecule with given B and D constants. And then the only thing which appears here as new is this degeneracy factor. Maybe it leads too far where it comes from, but that gives you the number of different states that have the same energy. And that is here in the rotational sublevels 2J plus 1. For example, if the lowest rotational quantum number J equals 0, you would have here 2 times 0 plus 1 would be simply 1. If you're in state J equals 1, you would have 3. If you would be in the level J equals 10, you would have here 21. So this degeneracy factor is an important part to really calculate the Boltzmann fraction, meaning the number of molecules in your probe volume which are in one specific rotational state relative to all others. And if you now plot these Boltzmann fraction over the rotational quantum number J, you would find for a given temperature a unique distribution of this population, meaning that you would have a maximum for a given temperature. That would be here, I don't know which number that is, maybe 10 or so, but that, let's say, distribution would change if you go for other temperatures. And let's say we go here from T1 to a temperature, let's say, which is higher in T2, then you would end up with, I don't make it very thoroughly, but you would end up with a Boltzmann distribution which is shifted to higher J values. And if you now spectroscopically are able to probe this distribution of the Boltzmann fraction over the rotational quantum number, then from this distribution you can directly deduce the temperature without any calibration. And that is the charm of this method. Okay, so that means as well, if you look for the differences between the energies of adjacent rotational states, that is in the regime of a few wave numbers. And that is a unit in spectroscopy very often used in the spectral range we are working. These are inverse centimeters. That is a measure of the energy. Yeah, it's maybe to one or the other not really familiar, but that has appeared due to, I would say, historical reasons. Okay, now we switch from the rotational to the vibrational eigenstates. Here, for a diatomic molecule, you find now the Boltzmann fraction given as function of the vibrational quantum number, which is now V, according to the energy levels of this vibrational state. And I go back. That is to be calculated by this expression over here. For a given molecule, you know the constants omega E, Xe, and Ye, and with that you can calculate these vibrational energy levels, and the degeneracy factor has disappeared. It is simply 1 for vibrational states in a diatomic molecule. However, the energy separation between adjacent vibration levels is rather large compared to the rotational degrees of freedom, and that's why you need rather high temperatures that vibrational levels are excited in your sample. And that is shown here schematically, at least for nitrogen, where the gap, the energy gap between the ground level of vibration and the first excited level of the vibration is in the order of 2,300 wave numbers. So you need a rather high temperature such that not only all molecules are in this vibrational state, ground state, you need at least something like, if you have here the distribution in the ground state, you need something like, let's say, 500-600 Kelvin, such that a certain fraction of your molecules is vibrationally excited. You have an idea how that works? It is not as that all molecules are at the same state. Yeah, that is the result of statistical physics. You have a distribution. That is like in gas dynamics as well. Yeah, you have not only, if you have a certain temperature, then all your molecules are not only having only one translational kinetic energy. They have a certain distribution given by the Maxwell-Boltzmann distribution. Here, that's the identical idea, but it's devoted to the internal degrees of freedom, not the translation, but here, in that case, the vibration. A typical number of the energy gap, as I said, is not like in rotation in the order of a few wave numbers. It is in the order of 1,000 to 4,000 wave numbers. So much higher energy levels than in rotation. Let's refer to electronic sublevels. Now we have here the Boltzmann fraction for these different electronic states with the accordingly the energies of these electronic excitations. And there the energy separation is in the order of at least 10,000 wave numbers for molecules we're interested in. And that's why they're, even at adiabatic flame temperatures, they're not significantly populated. That is maybe a side mark. So based on that explanation, maybe it becomes clear why, for example, CH star chemiluminescence is good to monitor a heat release zone. CH star would be not excited through temperature. If you have, let's say, in the post-flame region, and maybe I should make a drawing. Maybe that's if you have here space coordinate, and if you have here, for example, the temperature going from ambient to adiabatic flame temperature, then you would have here in this region, in the post-flame, although you have something like 2000 K, the electronic excitation of CH would be 0, yeah? But in the flame front, it deviates from that, if this is CH star, only because of the chemical reactions. So the chemical reactions have intermediates with electronic excitation. And they do not last for very long. One reason is they are, of course, very reactive. The other reason is they are now in an excited state, and the probability that they relax very fast is extremely high. And that's why in the post-flame zone, you will not see any chemiluminescence from CH star or OH star and molecules like that, okay? And that is because the electronic energies are separated by a huge amount, a huge energy gap. All right, so there are some exceptions, but that is maybe too much detail, and I'm not able to discuss that here in this lecture as well. So from this, let's say, discussion, we can say that the best way seems to be to measure the temperature by using the distribution of the rotational quantum states. That is the most suitable way. And so we can ask ourselves now, how do we do that practically? Also, we go through all these different ranges in the spectrum and see whether the technique is suitable or not. So the task, once again, is to measure the Boltzmann distribution of the rotation sublevels. And we do that here with a so-called single photon resonant process for the moment, meaning that we do have here light with a certain frequency. You multiply that simply with the Planck's constant, and then you have the energy of a photon, which is viewed as a particle without any, well, let's say, given a particle. And then what you do is, once again, you shine that in, and you, with a certain probability, bring your molecule from an initial state to a final state. And if this is now a certain rotational level, and this is another rotational level, then this energy gap is in the range of microwaves. It's a couple of wave numbers. And that means, in principle, you could use microwaves directly. The problem is, it is not common in combustion diagnostics, because if you have now microwave radiation, they cannot be focused very well. That is one reason why the spatial resolution is not very high. Others are problems due to background radiation, for example, such that no one, at least I know of, is using microwave spectroscopy to directly excite these rotation levels. Okay, but in principle it's possible. So in the exhaust of, for example, where you do not need a high spatial resolution, in principle microwave radiation could be used to probe that. Let's switch now. We go now to the next higher level, where we as well excite vibrations. So you never can separate that, because each vibration level consists of many rotation levels, and that's what we are after. We want to probe the rotational distribution. So the next possibility is to do rotational vibrational spectroscopy, where the range of energy gap between the ground level of vibration and the first excited level is in the order of here 1,000 to 4,000 wave numbers, which is in the infrared. So an example I give you here from HCl, taken from a textbook, and what we're looking at is a simple device for absorption, where you have here an infrared laser that can be tuned in its wavelength, where you measure the initial energy, and after a path length, where you have here in between HCl at homogeneous distribution, you measure the outgoing intensity with an appropriate detector. And we come back to this formula in a second. This is based on Lambert-Beer's law, which links here the initial energy I0 with the transmitted energy with the absorption length, and here the absorption cross-section, the probability that these infrared photons are absorbed by HCl. And if you then tune your device, you would find here the transmittance, meaning high transmittance over here, low transmittance where you have these peaks, giving rise to this nice spectra of HCl that we will discuss in a second. So first of all, before we can discuss this spectrum, you have to be aware that, again, without any proof here, but you have to know that we do have so-called selection rules. They're coming from quantum mechanics, and they give you information about the allowed transitions. For example, if you have, let's start with the J levels, with the rotation numbers. In almost all cases in infrared spectroscopy, the J level can change only by plus or minus 1. An example, if your initial value is, for example, 2, then you have two possibilities that your final level after absorption is either 1, that would be the a P line, or your final rotational level is 3. That would be a so-called R line that are distinguished. So this is really good, because of that, our spectra of these easy molecules are not heavily overloaded by lines, but you find only a finite number. For the vibrational number, there we do not have, for these anomalic potentials, similar strict rules. There, the vibrational number in principle can change not only by plus minus 1, but as well by higher values. Okay, and that means if you now restrict ourselves to the most of the molecules where you have either plus or minus 1 in the change of the J level, you find here a sketch of the spectrum in infrared spectroscopy. So this upper part over here, that is your final vibration level. Let's say that's 1 after excitation. This manifold is your initial vibration level. Maybe you start here from 0. Here is a large energy gap. That's why here we have the dotted line. In between these two levels, for nitrogen, it would be 2,300 wave numbers. For example, for other molecules, it's in the same order of magnitude, whereas the separation between the rotation levels, as I said, is a few wave numbers only. And then let's follow up what we have. We have here the so-called R branch, that is the manifold of all lines that have the selection rule delta J plus 1. let's follow 1 for example, if you have the R6 line that goes from 6 to 7. Or if you have here the R5 line from 5 to 6. And here you have the P branch, and that goes with delta J minus 1. If you go for the same from the P6 line, for example, it starts from 6 and ends at 5. Or it starts at 5 and ends in 4. Oops, or is it 5? Here, with 4. So you got it? This is the spectrum you can follow, and you can go back to what you see over here. Now we understand we have an R branch, we have a P branch. The R branch starts at J0 because it goes from 0 to 1. The P branch starts from P1 because it goes from 1 to 0, and there's no value below 0 in the J number. And the most important for thermometry is now that we do have here a certain distribution. I draw here an envelope, and this envelope, that is solely a function of the temperature. Here you find hidden by this relative line strength, that is the Boltzmann fraction behind. And so this is the way how we deduce the temperature. Measure at least two of these lines, you get the ratio, and out of the ratio you can deduce the temperature. Maybe you have an idea why it's better to measure only more than 2 lines. Why do you think it's better to not only, let's say, take the ratio of this line and this line?
Reduce your error.
Reduce your error. And which error? Is it the accuracy or the precision? Precision. Accuracy comes from the Boltzmann distribution, and precision is a statistical error. And because if you do these experiments in a rather short time, and you have only, let's say, a microsecond to measure, you have a certain noise on these 2 lines, and if you have 2 noisy quantities divided by each other, you end up with a noisy result. And it's improved if you measure as many lines as possible, and later on we will see in, for example, coherent anti-Stokes Raman spectroscopy, you will measure the whole branches such that you can deduce the temperature relatively precisely. Okay, what do we see as well from this spectrum? Between the R and the P branch, there is a hole that is called the zero gap, and that tells us there is no Q lines. You see directly in the spectrum that quantum mechanics makes a correct prediction. Lines where you go from the vibrational, the initial to the final state without changing the rotational number are not allowed. I go back. This was here. The Q lines, delta J equals 0 for HCl and most other molecules, they are forbidden. They don't appear. And that is hidden here in this zero gap. And what you can see as well, for HCl, you see all the time these double structures. This is not a single line, but this comes from the fact that you have isotopes that are occurring naturally, and if you have an isotope, you have more neutrons, and thereby you have a different mass, and because the rotational constant, I haven't mentioned that yet, the rotational constant, which is used to calculate the rotational energy, we have seen that this was this B value for a given vibration level, J times J plus 1, and then we had this correction here. This B level, that is proportional to 1 over the mass of your system and the distance between the 2 nuclei. Yeah? And if the mass, that's badly written here, maybe I should do it again. This mass is changing if you have a different isotope. Yeah, if you go from 35 to 37 chlorine, this mass is different, and as well there will be as well a different bonding distance, and that's why in the spectrum you can see the appearance of the isotopes very clearly. Okay, well that's just a side note for us. The important message is the envelope of this spectrum is a direct access to the temperature. Yes, please.
So when you do your measurements and then try to get the envelope, so do you still need to, so how much prior knowledge do you need to know about the molecule so that you know, okay, this part is the P part and this part is the R branch, and there shouldn't be any.
Yeah. So the question is how much pre-knowledge you know to reduce the temperature. In other words, you have to know where you are in the spectrum. And so what you do, there are different options. Maybe you're well equipped and you have a great wave meter with which you know exactly where you are. That is very unlikely because you need a very accurate system with a sub-wave number resolution. The more probable, the higher probability is that you just have a laser and then you tune over it and then you go to your database and try to fit the theoretical spectrum to your measured spectrum. And because these distances are unique, you can very easily identify where you are. But if you have, let's say, another molecule that would have an absorption structure overlaying that, then it can be more complicated. Yeah, and that means in some cases it might be not so easy to identify it if you have interferences from other molecules. But if you leave them away for the moment and say in this area you're sure that you don't have any interferences from other molecules, then you do the calculation, a simulation of the spectrum, and then you know where you are. Because these distances, as you see here, they are getting smaller and smaller for the higher R line levels. Here on the P lines, you see they are getting larger. Any idea why? That is due to the fact that your rotator is not rigid. And if you have a higher J level, then you have a higher probability for a larger distance. R is increasing, B is decreasing, and that influences directly your energies. And that means if you go through that in with more time, then you would find that the R lines are getting closer and closer to each other, and the P lines, they have larger and larger distances. And because of that, it's relatively easy to identify where you are on the spectrum. Okay? Good. Yeah. Now, we can, where have you been now? Of course, this was, oh, sorry, I know where we are. This was now to get the Boltzmann distribution over the infrared spectroscopy, raw vibrational spectroscopy. Of course, you can try to do that as well, including electronic transitions. And now we switch to a spectral range with higher photon energies, the UV or the visible. And there you not only change the vibration number eventually and the rotational states, but as well you change the electronic state. And that is because of the energy separation given here again at higher photon energies, typically for us in the UV. Here as well you do have some selection rules, and this is only an extract. Again, you have a selection rule concerning the rotation number. It's not only plus minus 1, which we identified with R and P lines, but here as well delta J equals 0 with the Q lines are allowed. And as well you do have here for the vibrational, the change of the vibrational quantum states, more or less no rule, everything is allowed. But from the electronic state you have another set of selection rules, and here is only given a few of them. And I guess we have no time to go through that. That would need a couple of hours of additional lecture to explain what this quantum number lambda, this quantum number S given over here really mean. Maybe all what you would need to know is that this so-called multiplicity for absorption is not allowed to change, and this lambda value over here gives rise, if you look, for example, for molecules like OH or NO and so on, you would find transitions where you have these Greek symbols P and sigma. For example, such a transition would be allowed, others would be not allowed. As I said, I cannot give you all the details to explain, but if you identify a molecule of interest and you might find something like that, then you have to open textbooks and read on yourself why this actually, where it comes from. So it's, for me, it's not so good to explain it like that. I would really prefer to have here a blackboard and do this, but that would need, I guess, at least 5 hours. So we have no chance. But if you just accept that we do have these selection rules, you can find now for a given molecule allowed transitions from the electronic ground to the excited state, where you eventually change as well the vibrational quantum number, and where you have the rotation substructure with the P, the Q, and the R lines. Once again, delta J is here, minus 1, 0, or plus 1. And this gives rise to 3 branches. given here schematically. Here's the rotational number from which you start. Here is the energy of the according level. And then you have here the R branch, R0, R1, R2, and so on. And if you would follow that up, you would get this behavior, and that is specific for these R branches. They have so-called band heads, that for higher rotation numbers, you find they go first to higher energies and then to lower energies, so you find something like that. And in this case, we do have this R branch at the high energy end. The energy goes from right to left. And again, because of Boltzmann distribution, you find the different lines have different intensities in absorption. You find the same for the Q branch, which is given here as well, a certain distribution because of the Boltzmann distribution, and the P branch over here. And now you can select possibly the R branch and do absorption spectroscopy in the UV or visible, depending on the molecule. And here you see an example of OH. So OH is a very prominent radical in combustion research because it's formed in the reaction zone, and it's used very often for flame front marking, although it exists as well in the post-flame region because at high temperatures water vapor dissociates, and at lower concentrations there you will find as well OH. Then in the convention we have in spectroscopy, the excitation goes with this arrow in absorption from right to left, and we start from the electronic ground state X and go to the first electronic excited state A. And the symbols 2 pi and 2 sigma, as I said, I cannot explain. This is the multiplicity, it's not changing, and pi sigma transitions are allowed. And then what you see as well is here to the right-hand side the denotation of the vibrational states. For example, we excite from 0 vibrational state to the first excited vibration level in the electronic excited state. And then we go through the R branch that is shown over here. I calculated that here for 18 bar, forget this N for the moment, and did this for different temperatures from 1400 to 2600 Kelvin. And you find now in different colors this absorption spectra. And because of the Boltzmann distribution, you find, for example, these features here, they are strongly dependent on temperature. Others, like this one or like this one, for this molecule, they are less sensitive to temperature. They are almost do not change. So if you're now interested to use one of these transitions, or at least two of these transitions, to deduce the temperature, you must know about the spectrum, you must know about the temperature range, and then you identify good transitions that can be used in the Boltzmann distribution to calculate the temperature. Okay. Now we come to the methods. So we know now, to summarize, the best way to probe the Boltzmann distribution is to use rotational levels. You do that either in the infrared, including vibrational transitions, or you do that in the UV or visible, including not only vibrational changes in vibration levels, but as well changes in the electronic states. So let's go through the methods that can be used in principle. Laser absorption spectroscopy is one choice. The second is laser-induced fluorescence. The third is Raman spectroscopy, and the fourth is coherent anti-Stokes Raman spectroscopy. All of them have a potential and are used in combustion diagnostics. So we go through them. And please ask questions or stop me if I'm too fast, or tell me when I'm too slow. Yes, please.
Please can you explain why you think that the rotational aspect should be the one to be used for?
Say it again, I didn't get it.
Why do you say it's rotation that should be used for that temperature determination?
Sorry.
You mentioned that rotation energy level should be used for temperature.
Yes, the rotational energy level should be used for probing the temperature, correct.
Why is that?
Why is that? Okay, I got it. Why the rotational levels? You have between the different quantum states a certain energy gap. If this energy gap is large, then the population of the upper level is very low. I'll give you an example. Let's say we have a CO molecule. Let's say we have a temperature of 300 Kelvin. Then you have, if this is now vibration levels, then the separation, actually I forgot it, it's in the order of 2000 something wave numbers. Yeah. Then at 300 Kelvin, you would have something like, I would say, I make a guess now, I have to calculate that precisely, but to illustrate that, you would have something like 99% of the molecule in your probe volume would be in the vibrational ground state. And only, let's say, 1% or less would be in the vibrational excited state. And that means if you now try to probe that by from absorption from this state, there would be a strong absorption, it's heavily populated. Do the same for the vibration excited state, there are just a few molecules. And that gives you a very, very tiny signal. And that means that there's almost nothing to be probed, meaning that you have a large error in the practical realization. And that's why you wouldn't get a precise answer. Yeah, because there's almost no population. It is very difficult to probe that in a short period of time. Maybe I didn't explain that good enough. So it's very important to ask the question, is that clear now?
Yes.
And in rotational, because they are so much closer to each other, it's always, even at 300 Kelvin, at 200 Kelvin, it's always that you have a multitude of rotation levels populated. Okay? And that's the reason. Okay. Yes, please.
So if we're trying to deduce temperature from rotational level alone, we are assuming that vibrational and electronic states are in the ground level.
No. They can be as well populated to a certain degree if you kind of prevent that. Maybe we come back to that when you go to coherent anisotropic Raman spectroscopy. There you'll see then as well that you will not see only the rotation spectrum from the vibrational ground level, but as well from so-called hot bands, from the first excited vibrational, second excited vibrational level, so your spectrum gets broader. You will see that. And depends now on you whether you would like to measure the whole spectrum or maybe only one part. But you do not assume that. You do not assume that. And if you're in thermodynamic equilibrium, the temperature deduced from the vibrational states and the rotational states should be identical. Yeah, it is maybe not always given because these different degrees of freedom might relax differently fast. And so, but for the moment, let's say we have fulfilled this requirement of equilibrium, and then the vibrational temperature and the rotational temperature from these different populations, either in vibrational or rotational, would be the same. All right. Let's start with absorption spectroscopy. We have seen that already. You have a laser where you know the initial intensity, where you know after you tune that and after transmission through this probe volume, you measure the outgoing intensity. You know the path length. And you have to know as well the absorption cross-section. That comes from, in our case, from tables that are known, it's a known quantity for a given molecule. That is something we have to know beforehand. And then you can reformulate that Lambert-Beer law such that you resolve for the unknown number density of a molecule in a certain J level. These intensities, outgoing, ingoing intensity are known, the length is known, and the cross-section is known. And then you can see directly if this is fulfilled, you know the length, you know the absorption, you have these two measured quantities, then you, without any calibration, can deduce the number density of the molecule in a certain J level. And that can be used now in connection with the Boltzmann distribution. Now you do that with two lines. It's called two-line thermometry. And if you go through the simple math and throw that into the Boltzmann distribution, what you have to know are the corresponding energy levels that are probed in this two-line thermometry. You know about the degeneracy factor, and these numbers N1 and N2, they come directly from your measurement. And with that, without any calibration, in principle, you can deduce the temperature. I go back to that. Why do you think is that not good for turbulent flames?
Because you'd be pulling different temperature eddies into the same volume.
Yes, both answers are correct. So you have different eddies with different temperatures. You're inhomogeneous, such that it's a line of sight method. You integrate over this direction, and if there is a temperature variation, you have no chance to resolve it. So you would, so there's in this simple setup no chance to see when you have a high temperature here and there. You cannot distinguish that. You get a mixed temperature, and that is, of course, erroneous. In principle, you can extend that. As I said, having only 2 lines, and you make a ratio in the end of 2 measured quantities. If these are noisy quantity divided by noisy quantity is not very good. That's why it's maybe better to make to measure a full spectrum, and then make a spectral fit, as shown over here. That can be done if you have a well-known molecule where you have all this line strength and all the effects of line broadening, again, something I cannot discuss over here, then you're able to calculate that spectrum and you fit the temperature such that your residuum is as small as possible. Residuum means the difference between the calculated and the measured line. You see here as well some noise. There might be as well some structures underneath which are maybe not only noise, shown in the residuum over here, that maybe need some attention. But in principle, by that way, you can now, as using the temperature as a fit parameter, deduce the temperature itself. So laser absorption is very sensitive. It is accurate. You do not need, in principle, any calibration when you know the length of the probe volume. And you need all the information about line broadening. As I said, no details here. It can be even more accurate if you probe many lines, a certain part of the spectrum completely. You as well do have a very nice resolution perpendicular to the beam path, but the problem is it's a line of sight, as we just have heard. So there is no spatial resolution along the laser path, and that means it's only good for homogeneous distributions. Okay, and if you probe many lines, then typically if you want to do it with one laser, you need a laser that can be fastly tuned. And that is given by infrared diode lasers, for a few of them at least, whereas in the UV, for example, that is more difficult. Tune a dye laser, for example, or an alexandrite laser is not as easy as a diode laser. So I would say, in summary, it's great in laminar flames, but in turbulent flames, it is, because of this line of sight character, not so easily applicable. Okay, but if you're after, for example, applications in atmosphere where it's more or less homogeneous, or in exhaust pipes, then it's okay. Then it's a very good and strong system or way to do it. A question? Yes.
In computing the population NJ, it seems it is a function of the length between it's a function of the path length, correct?
It's a function of what?
The path length.
It's.
So how important is it for you to measure the path length?
Yeah, it's very important. So the question is, what you see here, you have to know the path lengths. Without knowing the path lengths, or if you have an error here, you directly transfer that to your measured quantity. So one possibility is if you have, let's say, a certain volume that can be as well, where it's not sufficient to just take a meter. Yeah. One possibility is that you flood this volume with a molecule, for example, where your laser can be tuned to. Let's say you have a molecule that can be taken from a gas bottle, and that has transitions as well in the region where you later will measure, and then do that for a given pressure and temperature. Then you know the number density, and then you do it backwards. You resolve for the length for a given cross section, which you still have to know, and then you can very accurately determine that. And that's typically the way, at least we do that. Of course, we measure it with a simple meter, but then as well, we flood it with a molecule that has transitions and which is well characterized, and then we do it in that way. Yeah, the other way around. Then we know NJ and deduce the length. Okay.
So what if you have any optical lenses or something? Is it like the optical path length, or is it physical path length?
You mean this X over here? That is in the end the optical path length. That's the optical path length. All right. So we have discussed that. Now we switch, because of the fact that it's a line of sight method, we switch gears and look for a different technique that allows for spatial resolution. And that is a very popular technique, laser-induced fluorescence. I'm sure you have heard about that. And I guess many of you, is anyone using LIF? I would be astonished if not. Oh, that's only a handful. I would have expected more. Okay, what you do is you use absorption, very often of single photons, but not necessarily. For OH, for example, it's a single photon that brings you from the electronic ground into the electronic excited state. Then there might be some relaxation before it fluoresces. And fluorescence means that the energy is released, at least during the fluorescence process, is released into a photon. And this photon is again specific to that molecule because the energy difference here is completely transferred to that radiation. And so if you have different energy gaps, you will have a different wavelength, a different frequency of your emitted fluorescence. Very often you have a redshift, meaning that you need a higher energy and a shorter wavelength for excitation than in emission. And maybe that is well important to recognize. You have here the following relation. The speed of light, which is a constant, is the product between the wavelength and the frequency. Frequency, let's take as nu, meaning if you have now here larger wavelengths in emission than in absorption, that means you have a smaller frequency. And that is because the larger wavelengths means in the spectrum more towards the red. That's why it's called as well red shifted. That is over here. So that's very often, not always, but very often the case. The upper state's lifetime is finite. So the molecule rests for a certain time up there before it fluoresces. And in typical, let's say for OH, atmospheric flames, the typical lifetime is in the nanosecond regime. And this lifetime is severely influenced by the surrounding. And that is the problem in laser-induced fluorescence. So we have to go, we restrict ourselves to a linear regime. Linearity means that the signal intensity here is linearly dependent on the intensity of your laser. And if you go through this formula, you will see that this problem with the lifetime appears up here. So first of all, the measured intensity of the fluorescence is measured locally with a certain resolution, different than absorption. So you do have the chance to do this even for inhomogeneous distributions. You need to know the absorption cross-section. You need to know as well, I didn't mention that beforehand, the overlap of your absorption cross-section and the bandwidth of the laser. Maybe I should explain that. If you do have, let's say, a laser that is spectrally broad, that is my hand, that is now in this direction spectrum, and you do have a transition which is spectrally very narrow, like my finger, then it's only counting the overlap between those two. And most of the energy here and here, which are not overlapping with the transition, they do not contribute. And so in the end, it's not only the intensity that counts in absorption, but it's the convolution between the bandwidth of the laser and the bandwidth and the shape of the transition itself. You got it? Okay, so that's why we do have this gamma factor over here. Then U in this context means the probe volume. Omega over 4 pi becomes clear in a second. In the end, fluorescence is isotropically distributed. So you excite a molecule, an ensemble of molecules, and they emit the fluorescence in a good approximation isotropically in all directions. And you might use a small lens over here, and then you capture only a small solid angle. And this is this factor, omega over 4 pi. And then you have a certain detection efficiency. Maybe your detector has a quantum efficiency of 10%. Only 10% of the radiation is really registered. And maybe you have as well optics that not transmit everything. That is as well a certain transmittance factor. And then we come to the problem. We not only have here a quantity, a natural lifetime, which is known for molecules, that is a very often listed quantity. The problem is that the total lifetime, the effective lifetime, that is dependent on the pressure, the temperature, and the species concentration. So I make here I mark all the quantities that are measured. This is measured. This is measured. You know the absorption cross-section. You know the convolution. You know, after calibration, the probe volume. You know the detected solid angle. You know the detection efficiency. You know the spontaneous lifetime. But what is unknown is this quantity and this quantity. That is the quantity of interest. But this is the problem. Because this total lifetime, that is a function of pressure. Maybe you know that. The temperature, that is something you want to deduce. And that is dependent on the species that collide with the excited molecule. So simply that is called electronic quenching, which is a process where you have the excited molecule and then you have from the surrounding molecules that collide, and by the collision they take away the excitation energy such that the molecule cannot fluoresce anymore. And so this is a very difficult quantity to determine. Okay, the setup is shown here. You have here your tunable laser. You excite the molecules in this region of interest over here, and typically using a filter and an imaging system, you then record it with a CCD camera, with a photomultiplier if it's pointwise. If you make a light sheet over here, you can do it as well in a plane. And to relax a bit, you can look at that video where we have here a Bunsen flame. So a very simple thing somewhere down here, and that is operated partially premixed, such that a part of the natural gas already contains some oxygen, not sufficient to burn completely. And then you see here, after UV excitation that has been done with a 248 krypton-Freud laser, you see here some fluorescence independent of the wavelength given by the red line over here of C2 radicals. They absorb over a large range. And you see here to the left-hand side as well a bit of fluorescence color-coded from hot oxygen. And now what we are after OH fluorescence. So we tune now the laser, and that is done over here. And I stop the laser when we hit an OH transition. So first of all the time you see C2, all the time you see hot oxygen. Outside, of course, there's air. And when I hit the resonance, I stop, and the camera sees intensities, which are color-coded. So black is almost no intensity, and red and white is very high intensity. And I try to stop it at a good position. And then, oops, too early. Something like that. Then you get OH fluorescence, which is here just qualitatively. We have, making this quantitative would mean that you have to know the total lifetime, which is not easy to access. But yeah, I would like to take this as well as an opportunity to explain why LIF, at least monitored with an intensified CCD camera as done here, is not so easy. So what you see, for example, are changes in the intensity from here to here, which is simply amplifier noise. Yeah, this is completely unphysical that you have a higher fluorescence over here compared to here. So these devices are prone to amplifier noise. And that means to get rid of that noise, maybe you have to smooth it. Again, you have to relax your spatial resolution and somehow use a low-pass filter. Furthermore, you see here an area where you have a structure that seems to be thinner in the OH, completely unphysical. Why should it be? So this is simply due to the fact these images have not been corrected for the laser intensity profile. This kind of excimer lasers, this is due to their design. They very often have in the center, because of an unstable resonator, they have lower intensity at the center of their light beam. And you need to correct for the laser intensity. Without that correction, you would not be able to deduce any quantitative numbers. So that means it's not so easy actually to turn that kind of information, which is qualitative, into a quantitative information. It's very strong to mimic or to see where you have here zones of OH that can be used for marking a flame front, for example here in this rich part, for example here on the lean part, but making this quantitative is quite an effort in terms of concentration measurements. In terms of thermometry, it is not as bad, because we'll see that in a second. at least you have to excite now 2 different transitions. But if you do this in a turbulent flame, I go back here, maybe you have selected this line and this line to do your 2-line thermometry. In a turbulent flame, you have to do that quasi-simultaneously. And that means you need at least 2 lasers. Lasers that are tuned to this and this transition, and then which are fired maybe with a separation of a couple of 100 nanoseconds, and 2 cameras synchronized to this laser pulses, and then you get 2 images quasi-simultaneously, from which you then, by 2-line thermometry, building the ratio, getting an estimation of the temperature. So this is not as simple, and it's not a simple and not a cheap experiment, but in principle doable. So following the same idea as before, you have a measured quantity which is proportional to the number densities of the first and the second probed lines. But of course, you have to select them wisely, and that brings us back to the reason before. They should be sufficiently populated that your noise is not too high. And then you take the ratio, and that is done over here, which is an expression where you have calibration constants. You have to know the local laser intensity. You have to know about the characteristics in terms of degeneracy factor, the energies of your levels that are probed, the absorption cross sections, the overlap of the laser. You have to know the spontaneous lifetime. And now we come to it. This ratio, of course, depends as well on the effective lifetime. And people using that technique, they just simply say, and that might be valid or a good assumption for some of the molecules, it's not so bad, saying that this ratio is nearly 1. Yeah? And then because the effective lifetime of different excited levels are not so different, these cancel out in thermometry. That is at least in, I think all the papers, at least I know, using that approach, it is assumed. Because measuring that effective lifetime would blow up your experimental effort tremendously. Okay. Anyhow, if you do that, you're still in 2-line thermometry. You have a low precision because you just take the ratio of 2 measured quantities, which are there on their own are noisy. Of course, you could do better if you would use 3 lasers or 4 lasers and do 3 or 4-line thermometry, but because that's not practical, no one has done that. In principle, you can as well, if you do it in laminar flames, you can do that with multi-line thermometry, where you then measure an entire spectrum and fit then a theoretical spectrum to your measured spectrum with the parameter temperature as a variable. In principle, that can be done. Or method number 2 is if you plot your peak intensities in a logarithmically over the ground state energy, you get a slope which is proportional to the inverse temperature. Still, you have the problem here that the different states might have different lifetimes, and it would need a lot of effort to correct for that influence. Okay, but this is great in laminar flames, or applicable in laminar flames, where you have stationary conditions given, and then you can do this line scan, which take maybe half a minute or 10 minutes, depending on the discretization and the number of lines you're probing. Okay, so in turbulent flames, that is not easily applicable. Yeah, what about the choices of molecules? So you can use, for example, naturally occurring molecules like the OH radical. Then, of course, you're restricted to the post-flame zone and to temperature regions above 1500 K. But as well, you might be able to put in molecules like NO that are seeded to the flow and from which you can hopefully assume that they are chemically inert. That might be not true in autoignition. There, NO changes autoignition times. But that is a choice that people have used. But the percentage of NO to be seeded is not small. We're not talking about 1 ppm. We're talking about hundreds of ppm typically. And other people have used indium chloride. That is, has been used, for example, in gasoline engines where indium chloride has been dissolved in the fuel, isooctane. And then that is, this indium chloride is formed in the flame front the indium is formed in the flame front because of dissociation of this molecule, and then can be used as well to probe the different population states and deduce the temperature from the Boltzmann distribution. So in principle, here you have as well different choices of seeding. Okay, any questions about laser-induced fluorescence thermometry? Then we switch to the next choice, which is Raman spectroscopy. That is a very, very different process. So far, we have seen only resonant processes in absorption and emission. Resonance in that terms means that you do have a laser radiation and absorption tuned that the energy of the photons is matching the energy gap that is needed for excitation. Yeah, this is resonantly, you have in absorption here, you choose your wavelength, your frequency such that it fits exactly the gap between two energy levels. If you refer to Raman or Rayleigh spectroscopy, this is a very different process. This is a scattering process where you change or where you induce a polarization. So maybe I should make a brief explanation about it. In that process, it's explained best on using classical physics. Here, the light is viewed as a wave, electromagnetic wave. So we concern only the electrical field component. So your electrical field component in a wave is changing its amplitude. It goes from 0 to E0 to a certain maximum amplitude and back. It's doing that in a certain direction. Yeah, and the direction of the E field is your polarization. And if this wave now hits a molecule, then the molecule is polarized. The electrical field puts a force on your molecule because you have a nuclei, you have electrons, and they are now seeing a force because of the electrical field. So the electrons are maybe pulled away from the nuclei, and in the next second they come back. And so this is called a polarization, which is induced by this wave. And once you have a dipole, minus and negative and positive charge that are vibrating against each other, this induced polarization itself is a source again for light, for another electromagnetic wave. And this can be seen as a scattering process. The wave comes, polarizes, and the molecule is the source of a new wave that goes in certain directions, not isotropically, but in certain directions with different intensities. And if the molecule, after the scattering process, returns exactly to the same state from where you, okay, this I have to do it differently, this explanation. When you do not have any energy transfer between the exciting wave and the scattered wave, then we can say that is an elastic scattering process. There's no energy transfer between the initializing wave and the molecule that scatters. You can have as well an inelastic scattering process where after the exciting wavelength and or frequency and the scattered are not identical, such that you have an energy transfer from the initializing wave and an energy transfer to the molecule. And it could be that afterwards your molecule is in a higher energetic state, for example, vibrationally excited, or it starts from a higher level and later on is in a lower energetic state, such that either the scattered light has a smaller frequency or a larger frequency. And this scattering process is called, in this case, where the frequency of the scattered light is reduced, that's Stokes. In the other case, where you have a higher frequency, that is called anti-Stokes. And that is shown here in, again, a more, it's not in a classical way shown. Here it's shown in an energy diagram. What you see here, this is the different levels of your molecule. That could be vibration levels, that could be rotation levels. And what you do in Raman and Rayleigh spectroscopy, you shine in a laser which is not resonant. Yeah? This means there is no allowed eigenstate over here. So then the only process that can happen is you scatter and immediately the molecule returns from this higher level back either to its initial level or to another level, maybe a higher vibrational level or rotation level or a lower one. And that gives rise to here the Rayleigh scattering that has the same wavelength, the same frequency as the exciting laser, or a lower frequency or a higher frequency between Stokes and anti-Stokes. Maybe that was not as well explained as I wished, but please ask if this is not clear. It's a non-resonant process. That's important. You can use any laser you have which is not resonant with the transitions in your molecule. Now we have to find out how this can be used for thermometry. Maybe that's something I will do before we have another break. Okay, there's a question. Good.
What is a non-resonant process and a resonant process?
So then again, the non-resonant process is one where you shine in a photon, a wave, that is bringing up your system to a state which is not allowed. It cannot stay there, and that's why it's scattered and maybe return back to the ground state. And I try to explain that when you have a wave, you induce a polarization. The molecule is doing that, and itself acts like a dipole, like a Hertz dipole, as a source of a signal, a radiation that is emitted away from that molecule and brings the system back to its initial state if it's an elastic scattering process. If you distinguish that from a resonant process, then your exciting laser is tuned such that you hit a resonance, meaning that you bring it from one state which is allowed to another state which is allowed. And here in the scattering process, you bring it up to an energetic level which is not existent. Yeah? This is virtually not existent, meaning that the system cannot stay in that energetic level. It must return back to an allowed state. And it returns either back to where it came from, and then the scattered radiation has the identical frequency as the exciting one, or it returns to another one, and thereby it sees a certain frequency shift. Okay, that gave me a good way to explain it again. Is it clearer now? Okay. Okay, we do have in Raman spectroscopy, now we are referring here only to the Raman side, to the Rayleigh side we come later. We do have here as well certain selection rules. And that is the outcome of the quantum mechanic treatment, that the data, the change in terms of rotational Raman is either 0, that is again the Q branch, or plus minus 2. Before in absorption it was plus minus 1, here it's plus minus 2. These are now called for plus 2 O branch, for minus 2 S branch. They are much weaker than the Q branch, and here you see an example of a calculated spectrum at 1500 Kelvin of O2, where you have here the Q branch, and here you have the S and the O branch, and there is some remaining lines. It's only true for a few molecules like oxygen. These tiny things over here, these are a bit of R and a bit of P lines over here. For completeness, I have added them. So selection rules, it's not completely true for O2. You have a little contribution as well from this P and R lines, but that's maybe a detail. And once again, if you would probe that with Raman spectroscopy, then you would be able to deduce the temperature from this envelope. Yeah? Ideally, take the full spectrum, but maybe as well taking only a few lines. In principle, but the principle is the same. Boltzmann distribution provides you the distribution of this thing. Of course, if you do that now, the experimental setup shown here is a bit different to a laser-induced fluorescence. First of all, you can use a fixed frequency laser. You do not have to tune for the resonance. You just take what you have, let's say a needle-yak laser, which cannot be easily tuned. And then you have here again the possibility from a certain probe volume to measure perpendicularly the Raman scattering with a detector, maybe a CCD camera. But what you need here is a spectrometer, because now you have to distinguish the different spectral locations of your scattered Raman signal. And that means you do need a spectrometer before detection. And very often this spectrometer is chosen in combustion diagnostics with a low resolution, such that you might end up here with a low dispersion Stokes spectrum, where you have here, we take, for example, the N2 line, or the branch. I magnify that over here. What you see is only the envelope where hidden are the different rotational transitions. So what you do is you have now a transition from 0 to V equals 1, like that. You excite, then you have the scattered light going back. And this is true not only for one vibration level, but you have as well the same happens for all the different vibrational rotational transitions that are possible according to these selection rules. So these small lines here are the different rotation substates that are probed. And because the dispersion is not good enough, what you see is just very often an envelope. If you really want to get access to these rotation levels, you would need a much higher dispersion. And that would kill a lot of signal. That is why it is not so easy to apply this technique to really probe that quantum states. So let me finish that. In principle, of course, you can do it differently. Without looking for the rotational sublevels, maybe you just take the vibrational levels. Yeah, you probe here the ground state, and you might probe here the first excited state. And look here for Stokes and anti-Stokes radiation. If you would do that, you have a huge energy gap in the order of, let's say, 2,300 wave numbers in case of nitrogen. So this would be large, this energy gap. And that would come on the expense that this anti-Stokes radiation, this scattering process, would be rather weak, because that would be not heavily populated. But in principle, you can do that. If you do that, as I said, for nitrogen, that's a way that can be applied, but only for sufficiently high temperatures, and we had that before, because the upper level in the vibration level is not very strongly populated. And that is shown again. We have seen that over here. If you have low temperatures, this is something like 300 Kelvin, this is something like 2000 Kelvin. This is the relative intensity of your spectrum with low dispersion. You would see here only scattering from the ground vibration level, and only at 500, 600 Kelvin, you start to see here some Raman scattering from the first vibrational excited level. Or if you crank up the temperature even more, you see not only the so-called first hot band, you see here the second hot band where you do the scattering from the second vibration level. Maybe I should make a drawing to better understand that again. So this peak comes from V equals 0 to 1. These levels over here, they come from, you start from 1 and you end up in the vibration level 2. And these lines here, or these bands, they start at the vibration level 2 and bring you to the vibration level 3 after the Stokes process. And so if you now take the ratio between these levels as probed, shown before, at low temperatures you would have no chance to get a good signal. For high temperatures, possibly you have a certain population such that you could use this for thermometry. Okay, but as I said, the other way is that you try to probe the rotational substructures lying below that, and that needs a high dispersion, which is here by far too low to see that, and that's why pure Raman thermometry using the rotation substage is not very often used. Okay. Maybe to test whether you have taken the main message, can anyone explain me why, if you go, let's say, from low temperatures to high temperatures and staying here with the band from 0 to 1, why is that branch getting broader? This is the Boltzmann distribution. higher J levels are populated, and that's why the envelope is getting broader, okay? And that is going on the expense of the highest intensity, and that's why as well you see if your distribution is covering a larger range of J numbers, it's going down. But the single rotation levels which are underlying here, they are not visible. So all these small rotation lines lying underneath are not resolved here. And that is typically the case in combustion applications where we do not use a very high resolution, because then the Raman signal would be even smaller. Yeah? Higher dispersion kills signals. Okay, so maybe it's time again, for a break, maybe another 10 minutes, so we can restart at 11:35, and then I'll try to explain to you a very powerful technique, coherent anti-Stokes Raman spectroscopy, which is very well suited for thermometry in the gas phase. Thank you.